Once you are to this point, what we're going to be doing is we're writing an equation of what's going on here. So the very first thing is that we need to decide if we want to use degrees or radians. Now in all of our previous graphs that we did, we always used radians. The reason we used radians was because counting from 1 to 6.28 or 2 pi, right, was a little bit better of a scale for my x-axis and it corresponded to my y-axis better. But now if I look at my x scale, in this scenario, my day are my x and my hours are my y. My days are going from 0 to 450. So I'm actually going to have my equation is going to be written in terms of degrees. So let's get that equation written out here. We know that we have y equals a sine of bx plus c plus d. We know that b equals 2, or sorry, that b value, right? Let's get that erased right here. That to get that b value, we have, or that period, it would have been 2 pi divided by b. But in this case, since we are using degrees, we're going to say 360 divided by b. Now I threw in kind of like a screenshot of my graph that I created from all those points. If I kind of start connecting the dots here, we're going to use this to write my equation. So the very first thing is I am going to get my midline and my amplitude done first. If I'm looking at my midline, I want to do my highest point and my lowest point added together divided by 2. So when I'm looking at my table of values here, for Toronto, so this is going to be different for your values. My highest point is happening at 15.3, and my lowest point is going to be at 9. So right here, I'm going to say 15.3 plus 9 divided by 2. Or sorry, this is not going to be A. This is going to be D. Let me get that erased because that's going to say like, where is my midline? What's the center of those two values? So my midline, when I get that, it's going to be about 12.15. And remember, these are for my values. Your values will be different based on the city that you chose. For your A value, if I know that my lowest point is 9 and my highest point is 15.3, 12.15 is halfway between. So I'm just going to say, what is 12.15 minus 9? And I get that my amplitude is going to be 3.15. So we're just filling out this part. Now, for the rest of this, this gets a little bit tricky. I know that my B value is going to be how much did I change. So I know that 360 divided by B needs to equal 365 because there are 365 days in 1 year. Also, if I go here, I see that I'm going all the way right from 9 back to 9 in that whole full year. So once I get this done, I'm going to manipulate some values. I remember that little trick that means I can switch the denominator with the equivalent, and I know that B equals 360 divided by 365. Last bit is the shift that's occurring, or this C value. Remember that shift that's happening is we're saying like how much right or left. My sine curves, remember they start at the midline, so they need to start at that midline. Ooh, another thing I just noticed is that midline goes straight in between my spring and fall equinox. Coincidence? I think not. Anyways, so let's get that point right here. I remember that spring equinox happened, or that midline happened, and that fall equinox happened at 80 days. So if we're shifting 80 days to the right, then I'm going to say that the C value is going to be negative 80 because that's 80 days right. So for my equation, or for Toronto, my equation, and remember you have to do this 3 times is going to be y equals your a value, so 3.15, sine of 360 divided by 365 x minus 80. And then right there we're going to do plus 12.15. And this is my best estimate at my equation of my sinusoidal curve. Now, the next part is asking you to go through. So I already figured out my sinusoidal function for 1. You need to do this to your other 2 cities. If you also chose to do Toronto, that's fine. If you chose 3 completely separate cities, then you need to do that 3 times and could not use mine for the first. Number 4 says determine the sinusoidal regression of the equations of the best fit for each city in your TI-84. So in your calculator, in your Desmos calculator, what we're going to do, not your Desmos calculator, on your desktop calculator, what we're going to do is we're going to use this table of values, and I'm going to go to Stat, Edit, and I'm going to fill out all my x and y values to correspond to your x and y values here. Alright, after I get all these values inputted into my x and y columns, what you're going to do is after this, you're going to go to Stat, arrow over to Calc, and then I want for you to arrow up till you get to this sine reg. What this does is it's going to fit it to a sinusoidal graph. So if I press enter, we can go all the way down here, and this gives me some values. Now, what I want for us to note is that these are all in radians. So when I write down this equation for my calculator, I get 3.07 sine of 0.017x minus 1.36 plus 12.17. And that's just taking all of these values, right, and plugging them in. And honestly, let me actually change this to be negative 1.37 just so I'm rounding appropriately. All right, after I get to this point right here, let's just check and see how well I did. I know that all these are in terms of radians. Your calculator automatically does that since that's usually the most efficient way to graph. So to convert these values to degrees, I'm just going to do that 0.017 and I'm going to multiply by 180 and divide by pi. And I get 0.97. Well, the value that I originally had was 360 divided by 365. Let's just see how well we did. And that's 0.98. So I feel like we did a pretty good job here. 3.07 is pretty close to 3.15. 1.37, so let's convert that. Let's multiply by 180. I'm just doing my conversion, right? And then dividing by pi. And I get 78.5. Pretty dang close. So let's get this written out right here. So this is 78.5, and then this guy was 0.97. Okay, so then the real equation is going to be 0.97x minus 78.5. And these y values, remember, don't have to change. So plus 12.15. So here was my real equation that I got from my graphing calculator when I ran that regression, and you're just saying that right here, this is real, this guy is approximate. This is the equation that we made up on our own, and they look V similar, which is very good.